All right, in the last video, we derived the derivative of inverse sine. Recall that that was equal to 1 over the square root of 1 minus x squared. And the way that we did that was we knew that y equals inverse sine of x was equivalent to x equals sine of y. And then we used implicit differentiation to figure out that y prime was equal to 1 over cosine of inverse sine of x. And then we used a right triangle to say that theta was the angle that had a sine equal to x over 1. And we used the Pythagorean theorem to find the missing side, which allowed us to figure out what cosine of theta was. That was the procedure that we used to derive the derivative of inverse sine. What I want us to do in this video is I want us to find the derivative of inverse tangent of x. But I want you to try this on your own first. So I want you to rewrite this. Instead of inverse sine of x, we've got inverse tangent of x. So I want you to take y equals inverse tangent of x and rewrite this relationship in terms of tangent instead of inverse tangent. And then once you do that, you can use implicit differentiation to figure out what the derivative is, and you're going to have it be in terms of a composition of a trig function and an inverse trig function. And then I want you to set up a right triangle that allows you to evaluate that composition of trig function and inverse trig function. I want you to pause the video right now and try to work that out. And once you either think you figured it out or you get stuck, you can unpause the video and we will go through it together. Or if you think you've got the answer, you can check your answer. So pause the video now, give it a try, and then come back in just a moment. Did you actually pause the video and try it, or are you just waiting for the answer? Go ahead, pause it. I'll wait. Okay, let's tackle this together. Let's see if we can figure it out. So we knew that we had y equals inverse tangent of x, and we can rewrite that as x equals tangent of y. Now, we need to use implicit differentiation to differentiate both sides of that equation. So we have d over dx of x equals d over dx of tangent of y. Now, the derivative of x is just 1, so the left-hand side here is easy. And then on the right-hand side, the derivative of tangent is secant squared. So we've got secant squared of y times y prime, because we know we have to use the chain rule there because y is a function of x. And then to get y prime on its own, we have to divide both sides by secant squared. So we've got 1 over secant squared of y. But remember, we don't want this in terms of y, we want it in terms of x. So wherever we see a y, we can replace it with inverse tangent of x. So this is actually going to be 1 over secant squared of inverse tangent of x. And that's our derivative, but we want to simplify that. And to simplify that, we're going to want a right triangle, so we can do the same sort of trick that we did before. So we've got our angle theta here, and we know we want theta to be the angle that has a tangent of x. X is the same as x over 1, and tangent is opposite over adjacent. So that's going to be x over 1 for the right tangent. And once we've drawn that triangle, that means that this angle theta is the angle that has a tangent of x. So we can replace inverse tangent of x with theta. So at this point, we have y prime equals 1 over secant squared theta. We can leave it like that, but there is one way we can make this a little bit nicer, actually. We've got 1 over secant squared. We know that secant is 1 over cosine. And so if we have 1 over cosine squared, we can just rewrite this as cosine squared of theta, right? 1 over secant is cosine. They are reciprocals of each other. So 1 over secant squared is just going to be cosine squared. Now, to figure out cosine of this angle, we're going to need to figure out the hypotenuse. And we know that the hypotenuse we can get from the Pythagorean theorem. 1 squared plus x squared equals the hypotenuse squared. If we take the square root of both sides, that tells us that the hypotenuse is equal to the square root of 1 plus x squared. So we can write root 1 plus x squared up there. And then cosine of theta is going to be adjacent over hypotenuse. So that's going to be 1 over the square root of 1 plus x squared, all squared because it's cosine squared. But when we square this whole thing, what it does is it gets rid of that square root in the denominator, and we are left with just 1 over 1 plus x squared as our derivative. So we now have the derivative of inverse tangent of x. And now that we've done 2 of these, I'm just going to give you the rest so you have them all in one nice place. All right, here we have our table of derivatives of inverse trigonometric functions. We already saw that the derivative of inverse sine was 1 over the square root of 1 minus x squared. The derivative of inverse cosine is actually the same thing except with a negative out front. That's easy. They're just opposites. We just derived the derivative of inverse tangent. We saw that it is 1 over 1 plus x squared. And the derivative of inverse cotangent is just the opposite of that, negative 1 over 1 plus x squared. And then I've also provided for you the derivative of inverse secant and the derivative of inverse cosecant. These are also opposites of each other, so that is really nice. We don't have to really memorize 6 different things if we want to memorize these. It's really just 3 different quantities and their opposites. I want to challenge you on your own to derive the derivative for inverse secant, see if you can go through all of these steps and figure out where 1 over x times the square root of x squared minus 1 comes from. It's a little bit of a challenge problem. But for now, we have these formulas for the derivatives of the inverse trigonometric functions, and we can now just use them anytime we are evaluating derivatives involving these functions.